Hello, today I'm going over Elements and Compounds lecture. So we'll introduce the idea of elements and how they're different from compounds. Okay, so the first image I have here is an atom, and an atom is made up of three different parts: electrons, protons, and neutrons. But this is one atom, okay? Substances in chemistry are categorized as either elements or compounds. An element represents the simplest form of matter, possessing a unique set of properties with examples like oxygen and hydrogen. So these are both elements or atoms, right? Oxygen, hydrogen. This is another example. So these are elements. Conversely, a compound is formed when two or more distinct elements are chemically combined in a precise fixed proportion, such as the compound sucrose or table sugar. So sugar is made up of multiple elements that are combined in the same way every time. This fixed ratio means that in any sample of sucrose, the proportion of hydrogen particles to oxygen particles remains constant. So again, if I take one bit of sugar and compare it to another bit of sugar, it's got the same proportion of hydrogen to oxygen, which are elements. The fundamental difference between these two types of substances lies in how they can be manipulated. This is the sucrose molecule, by the way, which we saw earlier, and it's made, each time you see that letter there, that's representing some element. So one sucrose molecule is made up of three different elements, but a whole bunch of each element. Elements, being the simplest form of matter, cannot be broken down into simpler substances through any chemical means. So we're not going to get something different by taking a half of a sample of say hydrogen. It's still going to be hydrogen. Compounds, however, can be separated and broken down into their constituent simple elements by applying chemical processes. For instance, the compound sucrose, which we had up here and talked about, can be chemically broken down into its other elements. So I could take this structure, break it apart into carbon, oxygen, and hydrogen from which it's composed. That's why it's a compound. All right. Physical methods like those used to separate mixtures are insufficient for separating a compound into its simpler constituent elements. Let's remember a mixture. Think of a simple mixture like chicken noodle soup. Well, physical methods, I can separate the chicken out simply by picking it out. That's a physical method, just picking out the chicken. But they're saying with a compound like our sucrose, we can't use a physical method. I can't separate it through a sieve. I can't just pick out the oxygens. It's going to take a chemical method to do this. All right, let's see. Breaking down a compound requires inducing a chemical change, which is a process that fundamentally alters the composition of the matter to produce new substances. So if I do this, I'm going to alter it. I'm going to alter the compound. A common way to achieve this is through heating, which can cause compounds like sugar, so this test tube has sugar in it, to decompose into simpler products such as solid carbon and water vapor. So we're heating up this table sugar, and it's turning a dark color because the water vapor is outgassing this way, and what's left is just going to be carbon. So it'll end up becoming darker and darker. The properties exhibited by a compound are generally vastly different from the individual properties of the elements that combined to form it. So what they're saying is like, we're going to compare like how does sugar behave to how does oxygen behave, because oxygen is a piece of sugar, but we'll find that they're not going to behave the same way, even though, you know, oxygen has oxygen atoms and sugar has oxygen atoms. For example, the compound sugar is a sweet white solid, but its elements, the three that it's made up of, carbon, oxygen, and hydrogen, have entirely different characteristics, like being a black solid for carbon, a flammable gas for oxygen, or a supporter of combustion like hydrogen. This dramatic change in properties is clearly seen when the soft reactive metal sodium and the poisonous gas chlorine combine chemically to form the harmless white solid known as sodium chloride or table salt. So you take two things that are very dangerous, reactive metal and a poisonous gas, you put them together and it's just table salt. So now we have changed it chemically, which means it's going to exhibit different properties. It is difficult to tell the difference between substances and homogeneous mixtures by appearance, as both can look like a single kind of matter. So there's definitely mixtures that appear to be just like a compound or even an element. One way to identify a mixture is to see if it exists in multiple versions, such as the different fat contents in milk or the various octane ratings in gas. These are different versions of the same product, telling us that it is indeed a mixture. Materials with a fixed composition are classified as substances. In contrast, materials that can have a variable composition are classified as mixtures. And then we got a little chart here that allows us to kind of do a flow chart between mixtures and pure substances and then continue to break those down. Common names like water and table salt fail to describe a substance's chemical composition, which is why chemists use a standardized system. So if you remember, salt is actually sodium chloride, but we don't call it sodium chloride, we call it table salt. But in chemistry, table salt doesn't really describe or help us in any way. This system employs chemical symbols to represent elements and chemical formulas to represent compounds. So what they mean here is, for an element, I can say Ca for calcium and O for oxygen. It's just a symbol to represent that element. The modern symbols for elements, based on a system developed by Jan Jacob Berzelius, that sounds pretty good, are derived from their Latin names. So some of these are derived from English names and some of them are going to be derived from Latin names. These symbols consist of either one or two letters. The first letter is always capitalized, so the C here is capitalized, the O there is capitalized. And the second letter, if it has one, if one is used, is always lowercase. So oxygen doesn't have a second letter, but calcium does, and it's always lowercase. While many chemical symbols seem to come from their English names, such as Ca for calcium and N for nitrogen, others are derived from names in other languages, like Latin, which we spoke about up here. You're going to find that a lot, which in some cases can be confusing. So gold is an element, for instance, right? But we don't use G for the symbol for gold. We base it off gold's Latin name, and the symbol is capital A, lowercase u. And there's some other ones, like iron is abbreviation, the symbol representing iron is F, capital F, lowercase e, because it's referring to the Latin name for iron. These symbols act as a shorthand to construct chemical formulas for compounds, like H2O for water, C12H22O11 for table sugar. The subscripts in these formulas are used to show the relative proportions of each element within the compound. So 2 is telling me I have 2 hydrogens. Always have 2 hydrogens in a water molecule. In table sugar, I'm always going to have 11 oxygens or 22 hydrogens. So it's the proportion in each compound. For instance, the subscript 2 in H2O indicates that there are always 2 parts hydrogen to every 1 part oxygen. And because this composition is fixed, a compound's formula is always the same. Water is always H2O. Okay, so that gets us started. We're just getting used to being able to read some of this stuff for chemistry, and I hope this helps. Let me know if you have any questions. Thanks.